Hello everybody, welcome back to the channel. And today we're going to be deriving one of the kinematic equations. We're going to be deriving specifically this kinematic equation, which tells us that our position is equal to x naught, our initial position, plus our initial velocity times time, plus 1/2 at squared. All right. And today's objective is to try and understand where it comes from so we can use it in problems justifiably, because we shouldn't be using equations if we don't know where they come from. So here we're going to use a little bit of calculus to understand where this equation comes from. First of all, let's try and imagine the situation that this equation models. This equation models a situation where you have an object that is accelerating uniformly. What that means is that acceleration is constant. So we have some object that is accelerating at a constant acceleration. That acceleration could be 0, it could be 5, it could be -5, it could be positive, -0, whatever. All that matters is that the acceleration is the same regardless of time. It is constant. And this equation tells us what our position is going to be as a function of time if we know what our initial velocity was and we know what our initial position was. All right. This function, or this equation, tells us what our final position is going to be if we know all of these variables, where t is the amount of time that's passed, a is our acceleration, and x naught is initial position, and v naught is initial velocity. So we're going to try and derive this equation just by understanding the situation it's trying to model. We're just going to use this model. We're going to pretend we don't even know what this equation is yet. We're just trying to model this situation, and we're going to use a little bit of calculus to derive this equation as a model for this situation. So without further ado, let's get right into it. All right. So that's a bit of a reminder. Let us remind ourselves that the calculus definition of velocity is equal to the rate of change of position with respect to time, or the derivative of position with respect to time. This makes sense because a derivative tells us the rate of change of something, right? And the rate of change of my position, how quickly my position is changing, is by definition my velocity. So in the calculus world, velocity is the rate of change of position with respect to time. Additionally, the rate of change of velocity with respect to time is equal to acceleration for the same reason. The derivative of velocity with respect to time, by definition, tells me how quickly is my velocity changing with respect to time. And we know that how quickly my velocity is changing with respect to time is by definition my acceleration. That's exactly what acceleration tells us, how much my velocity is changing. So in the calculus world, we can write these equations, and they're true, because by definition, velocity is the rate of change of position with respect to time, and acceleration is the rate of change of velocity with respect to time. Additionally, this might be a notation some of you are unfamiliar with, but I could write that acceleration is the second derivative of position, which seems kind of weird. But all that means is that, and I'll go to another slide and explain what a second derivative even is. The second derivative of x squared is 2. That's because the derivative of x squared is 2x, and the derivative of 2x is 2. So the second derivative of x squared is what you get when you take the derivative and take the derivative one more time, hence the second derivative. All right. So if we go back to our initial example, the rate of change of position is velocity, and the rate of change of velocity is acceleration. So by definition, for what we just outlined, the second derivative of position is equal to acceleration. So we can use this equation. We're going to use this equation in our derivation, actually, because we know we're trying to find, so let's remind ourselves, we're trying to find our position as a function of time. All right, we're trying to find some equation that tells us our position as a function of time. And we don't exactly know where to start yet, but we at least know that the second derivative of position is equal to acceleration. And what do we know? Our acceleration in the example we're trying to model is constant. So this is actually a pretty big starting point, all right? This tells us that whatever our position function is going to be, it's going to have a second derivative of whatever the acceleration is in this situation we're trying to model. And this is actually super useful. And what we're going to do is we're going to use this equation to backtrack to try and find the original position function. We're told the second derivative of the position function is a. So we're going to backtrack from that second derivative to try and figure out what the position function is on its own. All right. So let's go to the next slide and do that. All right. So first, let us remind ourselves the rate of change of velocity is equal to acceleration. So in our example, the rate of change of velocity is going to be equal to whatever our acceleration value is. Whatever the acceleration of our object is going to be the rate of change of velocity. All right. So the derivative of velocity is going to be equal to a, whatever the a value is, which means our velocity function is going to have to look like this. A times t plus some random number. And I'll explain what that random number is in just a second. The reason our velocity is going to have to look like this is because we know that the derivative of velocity has to be equal to a. And notice how the derivative of this is equal to a plus 0. The derivative of a times t with respect to t is a, and the derivative of a constant is 0. So the reason we have to add that constant at the end is because when you take the derivative of a constant, it goes away. So our velocity function could be any equation in this form, a times t plus c, some number. All right, and it's now our job to figure out what that number is going to be. And it's actually not that hard to figure out what it's going to be. All right, let's try and figure out. Actually, I'll write the equation. I'll give you guys a second to process this, and then I'll clear my screen and I'll write the equation at the top. All right, cool. So we've been given that our velocity is equal to at plus c. Our velocity has to look like a function in this form. The challenge before us is then to figure out what that c value is. All right, and we can actually do it pretty easily. Let's try and think about conceptually what happens when t is equal to 0. Well, when t equals 0, our velocity is going to be equal to that constant because a times 0 is 0, so v equals c. All right, so clearly we can see that at t equals 0, if at t equals 0, v equals c, that constant is going to have to represent our initial velocity because v should equal our initial velocity at t equals 0. So this constant, this number, is going to have to represent our initial velocity. So in summary, the velocity of the situation we're trying to model is equal to at plus v naught for that reason. And now we're halfway there. So we have v equals at plus v naught, and this models the acceleration of our situation as a function of time. You might recognize this as one of the first kinematic equations, and this is actually where it comes from. This is one of the derivations of that kinematic equations, but we're not trying to prove that. We're trying to do the extra step and try and find the position function. But here's the intermediary step. We figured out that the derivative of velocity has to be equal to that acceleration term. So velocity has to look like this. In order for that derivative to be what's the word I'm looking for? To be validated. You know what I'm saying? In order for this derivative expression to be true, our velocity has to look like this because the derivative of this equation will be equal to a. And we showed that when t equals 0, v equals v naught. So therefore, this constant has to represent v naught. So that's where we're at. All right, I'll clear my screen. And I'll write that v equals at plus v naught. All right, and we're trying to backtrack and find the position equation. All right, and we're actually really close because we know that the derivative of position with respect to time is equal to velocity. That the rate of change of position with respect to time is equal to velocity. So whatever our position function is, whatever it is going to have a derivative of whatever our velocity function is. This means that if we know our velocity is equal to at plus v naught, then our position function is going to have a derivative of at plus v naught. So we have to think of what functions have a derivative of at plus v naught. All right, and I'll tell you what it is. The functions that have this derivative look like this, and I'll explain why in a second. Okay, cool. So in order for this derivative relationship to be validated, that the derivative of position must be equal to at plus v naught, our position function must look like this. Because the derivative of the first term with the power rule with respect to time is equal to at. Because when you bring the 2 down, it cancels with the 1/2 and you get at. The derivative of v naught times t is v naught, and the derivative of a constant is 0. So our position function has to look like this, all right? Because we know the derivative of our position function must be at plus v naught. So we showed that the derivative of this is at plus v naught. Therefore, our position function must look like this. So we're pretty much almost done. All right, we know that our position is going to be equal to 1/2 at squared plus v naught t plus c. But we have to figure out what this constant represents similarly to how we had to figure out what the constant represents in the intermediary step. And we can figure out what it represents in the same manner. All right, when t equals 0, our position is equal to whatever that constant is because 0 squared is 0. 0 multiplying by 0 gives you 0 here. So when t equals 0, all these terms are going to be 0, and you're left with x equals c. All right. So if the constant tells you your position at t equals 0, then the constant has to be equal to your initial position. Because if x equals that constant at t equals 0, then that constant has to be your initial position by definition. Your initial position is your position at t equals 0. So that constant represents x naught. So we can rewrite this equation by replacing the c with x naught, because that's what the constant represents, and we get the final equation that x equals 1/2 at squared plus v naught t plus x naught. And if you want to rearrange it into the form that's more familiar with you guys, remember, it doesn't matter what order you add things. We get that x equals x naught plus v naught t plus 1/2 at squared. And that is exactly where that kinematic equation comes from. It tells you your position as a function of time, where x naught, v naught, and a are variables, preferably constants. But if you also know how much time has passed and you're trying to solve for one of the constants, you can do that too. In summary, all this equation does is relates variables. It relates position, initial velocity, and acceleration and time. That's 5 variables. Yes. 1, 2, 3, 4, 5. Yes. Okay, so that's what this equation does. And we just derived why it's true using some basic principles from calculus and a little bit of backtracking. That process, by the way, is an introduction to anti-differentiation, which is the process of being given a derivative and trying to figure out, I did not spell that right, anti-differentiation, I don't know. I can't really, math is my specialty, not English. But that was an intro to a process called anti-differentiation. I'll just write anti-diff. Because what we did is we were given some derivative. Let's say, we're given some derivative. And we were told that this derivative is equal to something. And we had to use this derivative to try and figure out what the initial function was equal to. And, hopefully the reason it's called anti-differentiation makes sense is because you're quite literally anti-differentiating, you're backtracking. So that was an introduction to anti-differentiation, and we used our basic calculus knowledge to understand why that kinematic equation works. So hopefully this video helped out. If you need any help at all throughout the year or anything at all, just leave a comment down below, reach out to me. I love to help. But hopefully you guys can now solve problems using this kinematic equation with confidence, understanding where it comes from. Thank you very much, and I'll see you guys another time.